Hello everyone, I am Shantanu Vyas and I will be presenting a paper titled ShapOrator, through which we enabled design iteration for young designers through shape verbalization. My collaborators for this work are Dr. Chen, Dr. Woodward, and Dr. Krishnamurthy. To begin this presentation, I will first talk about the motivation behind our work. Design iteration plays a significant role in the design process, where the designer goes through a series of steps, gaining more information about their design problem and gradually improving their solution. Sean described the design process as a reflective cycle where the designer sees, moves, and sees, and Hibbs et al. Described it as a series of transformation processes. The cognitive aspect of design iterations was also studied in depth by Adams and co. Therefore, enabling the iterative nature of the design process is very important for developing computational support tools. Prior works in computer graphics and CIE have embodied the principles of iteration and reflection, either in the form of sketching interactions or tangible and spatial interactions. However, for younger audiences with no formal understanding of the design process, these interactions might be hard to learn and adapt to. An interaction that has often been overlooked is verbalization, which has been shown to aid the learning process and improve cognitive skills in children. While there have been some prior works that use speech as an input modality in design tools, they either integrate it into a multimodal interface or as an extension to a CAD software. Therefore, in our work, the knowledge gap that we are trying to fill is a lack of use and study of verbalization as a direct means to enable design iteration. Taking inspiration from Sean's metaphor of seeing, moving, and seeing, and other works that have studied the importance of reflective verbalization, we first formulate the design interaction process of our workflow as a cyclic sequence of reflection, expression, and transformation, where verbal input is central to the entire process. Next, we create an interactive system called ShapOrator that enables 3D shape modifications of a template shape using verbal expression in real time. Our goal was not to create a feature-rich design software. Instead, we wanted to study how we could enable design iteration through verbal inputs and how it affected the iterative design process. Therefore, our system was specifically designed and constrained to help us accomplish these goals, which we did by using it to conduct studies with 10 participants. Now, I'll dive a little deeper into the system design and its considerations. Context plays an important role, especially in early stage design, where designers keep the context in mind while making certain decisions. As our users were middle and high school students, we decided to use spaceships as our design context, since they have been used in prior studies conducted on children. To make the students even more engaged in the design task, we further narrowed down the context to spaceships from Star Wars. Once the users familiarize themselves with the design context, the next action would be to verbally express their design intents. Therefore, our task was to convert the user's expressed intents into machine-understandable commands. For this, we classified the user's relevant commands into three main transformations, which were the cross-sectional shape changes, dimensional changes, and adding and removing components. An example intent for cross-sectional shape change would be to make the fuselage triangular. Our system needs to first identify the component in question, and then the shape that it needs to be changed to. Similarly, an example intent for dimensional changes could be to make the engines longer, where the component is the engines and the dimension type is length. In addition to this, our system should also be able to understand certain specifications, which in this case is a percentage by which the user wants the engines to be longer. Finally, an example intent for adding and removing components is to request the addition of more wings, where the component is the wings, the type of change requested is addition, and the specification is the number of wings to be added. If the user's commands don't fall under any of these transformations, the system makes no design modifications. Our next task was to convert the machine-understandable commands into 3D design transformations. For this, we used swept volumes as a geometric modeling technique, as they provide a convenient way to make design modifications by changing their constitutive curves, which comprises of the section, the guide curve, and the path. Using swept volumes, we were able to allow sectional-based shape and dimension changes, and also guide curve-based dimension changes. Moving on to the specifics of our ShapOrator system, we start with the shape template, which we created by taking inspiration from the design of the X-Wing from Star Wars. The template is a multi-component assembly where each component is created using swept volumes. The seat template comprises of one fuselage, or also called the body, two engines, two wings, and two missiles. The sectional shape of each of the components were generated using the super formula, through which we can generate a wide variety of shapes by simply changing the variables m, n1, n2, and n3. For instance, we can create a square or a four-sided polygon by setting the value of m as 4, which is the number of corners of the shape, and keeping the other variables equal to 1. Now, by reducing the value of n1 to 0.5, we can get a 4-pointed star. We therefore map the shapes and their descriptions to their respective variables. In addition to this, we also allow smoothing of cross-sectional shapes by using the Laplacian smoothing technique. Moving on, we have two main types of dimensional changes. The first being the section-based changes, where we added two scaling factors, s and t, to the equations used to find the x and y coordinates. By changing the values of s, we can get wider or narrower shapes, and by changing the value of t, we can get taller or flatter shapes. The next type of changes are the guide curve-based changes. By moving the control points of the guide curves towards or away from the axis, we can make the parts radially bigger or smaller. And by moving them closer or farther from each other, we can change the length of the parts as well. In addition to the shape and dimension changes, we also allowed users to add and remove specific parts. To avoid overcomplicating the design task, we introduced certain constraints. One constraint was that wings came in pairs of 2, and that each wing came with its own set of engines and missiles that the users could not individually add or remove. Users also couldn't manually change the location of parts. However, we integrated a change-aware part relocation feature. We now move on to the module responsible of understanding verbal inputs. Once we obtain the audio input from the user's design intent, we must convert it into textual data. For this, we use Microsoft Azure's cognitive speech services, through which we trained a custom speech model using the audio and text data from 8 individuals. Once we have the textual information, the next task is to understand the user's intents and classify it into one of the previously described transformations. We use Azure's language understanding module that allowed us to train a custom model built on top of a pre-trained NLP model. Finally, after receiving top intents and specifications, we provided the data to our shape modeling module that performed the design transformations. Tying all of these modules together, we created this interactive user interface that allows users to give verbal commands by holding down the space key. The UI clearly shows the labels of the parts that the users can modify, and also provides buttons for simple tasks such as resetting the shape and orientation, saving designs, or toggling the lasers and flames on or off. With this, we conclude our system design, and now I'll talk about the experiment design and our findings from the user studies. We conducted our user study during a university-hosted summer camp, where middle and high school students interested in STEM courses took part. Our lab conducted a 2-day workshop during the summer camp, where we gave the students a brief introduction of the design process that involved activities related to design ideation, prototyping, 3D modeling, followed by a user study, for which 10 students between the ages of 13 and 17 years had volunteered. Our study procedure started with a practice session for 7 to 9 minutes, followed by a study where we gave the participants an open-ended task of creating spaceship designs without any constraints. The study itself consisted of a cyclic sequence of the participant making design changes, and then the study administrator asking general questions regarding the design after every few major changes. Here is a snippet of our user study.
Make the wings shorter by 20%. Make the engines taller by 30%.
So are you set on the shape right now, or are you trying to find new sizes and see what kind of sizes fit best? So what is your plan with like either changing shapes or sizes?
I'm mostly trying to change the shape right now.
Okay.
To where it'll be a smaller sort of.
Okay, overall aircraft. Smaller.
Yeah.
And you associate smaller aircraft to what exactly?
Just because I mostly want it smaller, just because it's harder to hit a small, and I'm just sort of thinking about this like metaphorically. It's harder to hit a small fly than a big, maybe 6-inch cockroach.
Okay. So that was a snippet of our user study. Moving on to the quantitative findings, we found that the participants made an average of 68 changes using voice commands. The most preferred type of change was dimensional changes, and 6 out of 10 participants made the most changes to the fuselage, probably because of its central location and relative size compared to other parts, which might also explain why 7 out of 10 participants made the least number of changes to the missiles. Finally, here are the top 3 most preferred shapes for each part of the spaceship. While quantitative results gave us an overview of the general trend of the modifications, we were more interested in why participants made these changes. Which brings us to the qualitative findings. Here, we divided the users' responses to our questions into 2 broad groups, which are functional contexts and topical contexts. If the users' responses were motivated by the functionality of the spaceship, we classified it as a functional context. And if the users made topic-specific changes, we classified those into topical contexts. Both of these broad groups are further divided into specific categories, which we will talk about in detail now. The first functional context we will focus on is aerodynamics. An example for this is when participant 3 made specific changes to the design you see on the left that included making the body triangular, making the wings circular, and making the engine smooth. Reflecting on the design modifications, they said that they were going for a sleeker and a more aerodynamic look. This trend was seen across different participants as well, where 3 of them explicitly mentioned their desire to make their spaceships more aerodynamic. The next functional context was battle-related, where 4 participants associated their design changes as a result of making their spaceships more battle-ready. For example, here participant 7 added 4 wings and made them shorter, and this is from the video that you saw earlier. Their reasoning for this was their desire to make a smaller spaceship, as they felt it would be relatively harder to hit. Another functional context that was common across some of the participants was that of maneuverability and propulsion, which led them to make more dimensional changes as well as add more parts. An example here is of participant 9 adding 2 wings and making the body circular, as they felt that a bigger body required more wings, and since the wings came with their own sets of engines, that was also an added bonus. Moving on to our final functional context, which is human-centric design, what we realized was that most participants ignored the human-centric aspect of their design. However, when they were asked about it, they had some interesting insights. For example, here participants 5 made specific design modifications and then answered the human-centric question by saying that they felt it would be best for their specific design to be an unmanned spaceship, as they felt that it would be hard to fit people inside. Now, moving on to the first topical context, which is a storyline, we noticed quite a few participants made design changes specifically motivated by the Star Wars theme. One interesting example here was participant 4 making all the cross-sectional shapes of the parts a 5-pointed star, as they felt that everything should look like a star as it fits the Star Wars themes better. One of the most commonly observed contexts was a preferential context, where participants made changes just based on their preference, which a majority of the time was motivated by the visual aspects of the spaceship. So an example here is when participant 1 made their engines a lot smaller compared to the fuselage, as they did not want their engines to visually stand out. We saw similar preferential changes being made by almost all participants to make their spaceships look good. Finally, our last topical context is derived from the participants' past experiences. Here, the example involved participant 2 making their fuselage triangular and flat as they associate the flatness of the spaceship to pancakes. We saw similar approaches being made by 2 other participants who used their past experiences to make specific design changes. With this, we conclude our qualitative findings, where we try to understand the participants' verbally expressed design intents with the help of their verbal reflections. And here are the participants' final designs. As you can see, not all participants explore the same number of designs, which again was not a strict requirement from our end. I'll now talk about the feedback we received and the limitations and future direction of our work. The overall feedback we received was quite positive. Participants felt the design activity was engaging and it made them feel creative. Highlighting some of the general comments, participant 2 shared that they were fascinated by the number of changes they could make using voice commands, and participant 7 found the activity engaging and mentioned their desire for wanting to use their voice for different computational tasks. Some of the suggestions we received included the ability to change colors, allowing individual part modifications, and expanding the vocabulary. Moving on to our limitations, one of the major ones was our limited vocabulary, which we did to maintain a sense of simplicity. However, moving forward, we could use large databases such as WordNet or large language models such as OpenAI's GPT-3 to better understand user intent. Another limitation was the aspect of generalizability. We limited our studies to a 3D model of a spaceship, but moving forward, we could look at datasets such as ShapeNet to provide us with semantically similar objects, where we could implement a more general speech-based workflow. Finally, our system allowed a constrained set of modifications to prevent users from having to learn and remember a lot more commands. In future applications, we could easily implement a variety of geometric modifications to create a more robust designing software. Finally, looking at the future direction of our work, we could take clues from analogies used by people and focus on analogy-based iterations where the system could generate results based on the analogies provided. On a similar note, we could also predict the shapes and sizes of objects based on the user's desired functions, behaviors, or attributes. That concludes our presentation. Thank you for your attention. For more details about our work, please read our paper on the ASME website and feel free to reach out to us for any specific questions.